Hi, in this video we're going to be discussing our CS2100 tutorial 9, and what you'll notice is from this tutorial and the next and so on, we are now trying to solve a given problem using higher level uh, logic blocks. Okay, so earlier we saw how we can, just given an input output relationship, come up with a truth table, and then we simplify it, and for simplification we can use basic logic gates to design a circuit, okay, that solves the problem that we want. Now we're going to use higher level or more complex logic blocks to solve our problems or the challenges that we have. So in this first question, we are asked to design a circuit that counts the number of ones appearing in an 8-bit input. Okay, so if I were to write it out here, so I have A, B, C, D, E, F, G, H. Okay, and the example is given is 0 1 1 0 0 1 1 1. Okay, and basically what I want is to design a circuit that takes in these values, okay, A, B, C, D, E, F, G, H, and the output that I'm supposed to get is a 4-bit number PQRS. Okay, and you should give tell me the number of ones that are in the 8-bit input. Okay, so if this 8-bit value were actually applied to the circuit, okay, and the output here should be 5, okay, which would be 0 1 0 1. Okay, now how would I go about doing this? Okay, given this information that is present here. Okay, so of course if we don't have this information here, and we try to think of it in terms of what we have done in the past, we can say, okay, I can come up with a K map. I come up with a truth table with 8 inputs, all the possible combinations, and then I have 4 outputs. But you can imagine that a truth table with 8 inputs, I have 256 combinations, correct? So it is a very impractical thing to do. Okay, though even though it is possible, it is very impractical. Okay, so that is why now we are given higher level blocks like this, and what we are going to do is to count the number of ones using what is provided, which are the adders. So we are given full adders, one 2-bit parallel adder and one 4-bit parallel adder. Okay, whenever you want to count, okay, you always count based on adding the new value to the least significant bit of the current value. So you always add based on the lowest position, correct? Just like if I were to say 12, okay, just in decimal, if I were to say 12 plus 5, where does this 5 go? It goes to the least significant bit position, correct? So I'll say 7 and 1, alright? So you always add based on the least significant bit position. So since we know that's how we normally add in decimal, it's the same thing that we apply in binary as well. Okay, we go to the least significant bit. And a full adder, in this case, is a 1-bit adder. So the 1-bit adder is basically adding bit by bit. Okay, so what we're going to use is 2 full adders here. So 2 full adders. So the first full adder is having an input X, Y, and carry in here. And the other full adder here, okay, is another input here, X, Y, and carry 8. Okay, and what we can do is we can put the first 3 bits here, A, B, C, and the next 3 bits here, D, E, F. Okay, and for each of these full adders, you have 2 outputs here. Okay, one is your sum, the other is your carry. Okay, the other sum and the carry. Okay, so now let's see what is going to happen. Coming back to our example here, okay, we have A is 0, B is 1, C is 1, D is 0, E is 0, F is 1. So this is the example that is given. So if 0 plus 1 plus 1, what I should get is 2. So 2 is 1, 0, carry 1, correct? Similarly over here, 0 plus 0 plus 1, the answer should be 1, carry 0. Okay, so now you can see that these were all treated as single bit values, and after using the full adders, what I have are now 2-bit numbers. So what I have here are now 2-bit numbers. So I need to perform the next stage of the addition using a 2-bit adder. Okay, so you have to understand that the first stage, when we looked at A, B, and C, and D, E, F, we were counting them as single bits. Correct. So now that we have these single bits already added up, we have now two 2-bit numbers that represent the number of ones in A, B, C, and D, E, F. So if I look at it in A, B, C right now, I have 2 1. So this over here, okay, is 2. Okay, and D, E, F here is 1. But I still have G and I still have H. Okay, so what I need to do is I need to add the G and H again, not again, to these current answers that I have. Now, for the next stage, the 2-bit adders, how do I connect them up? So I have a 2-bit adder here. Okay, so this is a 2-bit adder. So for a 2-bit adder, I have two inputs, x1, x0, and y1, y0. Okay, and the output is s1, s0, and the carry. Okay, so the output is total 3 bits, 2 bits of the sum and 1 bit for the carry. Okay, and how am I going to connect them up? I'm just going to connect them up how I would normally do for 2-bit numbers. So this is the least significant bit, and this is the upper bit. Same thing over here. This is the upper bit, and this is the least significant bit. Okay, so for every adder, there's always a carry in, correct? So this carry in will be now connected to one of the remaining bits, which is G or H. So I can connect G over here. Okay, so again, like I said earlier, whenever we add, we always add to the least significant position for decimal numbers or binary numbers or anything. So by adding or putting G to the carry in, what we are basically doing is we are treating G as a single bit value. It's either 1 or 0. Okay, so it is following our convention of how we do addition. Always add to the least significant position. Correct. Now this output, okay, is now a 3-bit value. Okay, and now what I have is I can make use of the 4-bit adder. Okay, so how do I make use of the 4-bit adder? So I have a 4-bit adder over here. Okay, so for the 4-bit adder, I have two 4-bit inputs. So x3, x2, x1, x0, y3, y2, y1, y0. Okay, and since this is a 3-bit value, so this is the most significant bit, comes to x2, comes to x1 and x0, and x3 I can connect it to a 0. Okay, and y3 to y0 I can all connect them to zeros. So the only remaining alphabet, which is your H, okay, will be connected to the carry in. So again, the same principle as just now. Why we put it to the carry in is because we want to give it the addition to the least significant bit of the current answer that we have. Okay, so the final answer will be S3, S2, S1, S0 together with the carry out. Okay, and the 4-bit final answer comes out here, PQRS. Okay, so that is how you are able to solve this question here. So the technique will be repeated again in subsequent questions. So as long as you understand that using a full bit adder, I am able to count the number of ones that I have by treating each of the 8-bit numbers as each of the bits in the 8-bit number as single bit values, correct? And then I add them, and after that I cascade them to a 2-bit adder and subsequently to a 4-bit adder. Okay, and every time we move on to the next stage, the 2-bit or 4-bit adder, if you want to add in one more of the bits, we have to make sure it's in the least significant bit position, so we use the carry in. Okay, an alternative solution is I can connect this y0 to h and c in can be 0. Okay, so that is also fine, because if I connect y0 to h and y3 to y1 is still 0, then h is still in the least significant bit position. Okay, so that is also another alternative solution for this question. Okay, so I hope this is clear. uh, Again, do not be overly concerned if you are not able to figure things out initially, but what is important is after you get the solution and you sort of understand it, you should be able to now have an appreciation of how to use hardware blocks to solve problems, and then you should be able to be more confident in solving such similar problems. Okay, so before we go on, let's just finish up the numbers here. So previously we saw that for ABC there were two ones, and for DEF there's one. So this is over here what we have is a value of 2, and over here what we have is a value of 1. So 2 plus 1, and G has a value of, let's look back here, G has a value of 1, H has a value of 1. So G has a value of 1. So 2 plus 1 plus 1 will be 4. So what I should expect here is a value of 4. Okay, so if I were to write it out here, 1 0 plus 0 1, I will get 1 plus 1, then plus another carry in, which is G. So this is your G. So 0 carry 1, 0 carry 1. So this is 4. Okay, and your H is also a 1. So 101 plus a 1, so 100 plus 1, I'll get 101, which is 5. Okay, so this is your H. Okay, so the final answer that you get for PQRS is 0101. Okay, which is 5 for this example. Okay, so I hope this sort of makes it clear on how we can use the adder blocks, okay, to solve this problem of counting the number of ones that you have. Okay, now let's go on to the next question. Okay, in question 2, we are asked to implement a Boolean function that takes in two 3-bit numbers and sees if they are neighbors in a 3-variable K-map. Okay, so let's first understand this a bit better. So if I were to draw a 3-variable K-map over here, okay, so let's say it's A, B, and C over here. Now this is 0 1 0 0 0 1 1 1 1 0. Okay, so let's give two neighbors here, this and this. Now if we were to analyze these 2-bit patterns, okay, for A, B, and C, what we will see is, for example, this is 0 0 1, and the other one is 0 1 1. Okay, so we observe that for neighbors in a K-map, only a single bit will change. Okay, so in this case only B changes, okay, within that grouping. Now if I were to look at a K-map, okay, like this, okay, the same K-map, okay, but now we look at it differently, in a sense that we look at two other values. Okay, now if I were to look at this and this, for example, now the same A, B, and C, what would I have observed? I was seeing that their values are 0 0 1 and 0 1 0. So two bit locations have changed if they are not neighbors. Okay, so that is the first thing that we must understand. In order for them to be neighbors, okay, only one of the bits must have changed value between both the values. Okay, now what do we know about detecting a difference in the bits? We know that an exclusive OR operation, okay, an exclusive OR operation can be used to detect a change in the bit. Okay, so for example, if right now I have to do exclusive OR operation here, okay, so I have to do exclusive OR operation, this would have been a 0, this would be a 1, this would have been a 0. Okay, whereas over here this would have been a 1, 1, and 0. And if I were to count the number of ones in the result, I will get a value of 1. Whereas over here, I will get a value of 2. So what we can deduce from this analysis is that in order for me to know if two 3-bit numbers are actually neighbors in a K-map, I need to be able to do an exclusive OR operation bit by bit, and the final answer can only be one value, which is 1. Any other value beside 1 will be wrong. Okay, so I hope you understand the analysis. In order for us to deduce that two numbers are neighbors in a K-map, okay, I must be able to do an exclusive OR operation bit by bit, and after that I must be able to count the number of ones in the result, and the number of ones, the only acceptable answer is 1. Okay, so this is the only acceptable answer in order for me to deduce that they are neighbors in a K-map. Any other answer means they are not neighbors in a K-map. Okay, so now that we understand this, of course we can say I can use K-maps, sorry, I can use XOR gates, okay, to solve this, okay. But what you're given is, if I were to use XOR gates, I must have at least 3 XOR gates, okay. But the question says that you are only allowed 2 basic gates at most, and no more than 4 full adders, okay, no more than 4 full adders. So somehow just using XOR gates alone is not enough, and I now need to think of how the full adders will come into place, correct? Now let's look at the full adder internals, okay, that you have actually seen in your lectures. So a full adder has 3 inputs, X, Y, and C in, okay, and the outputs is sum and carry. Okay, let's just look at the circuitry involved for the sum. Okay, and if you look back at your lecture slides, you would have seen that the way the sum is generated is the X and Y have an exclusive OR, and the result is then passed through another exclusive OR before being sent out as the sum. So this is the internal of the full adder. Okay, which means that the sum is actually X, okay, exclusive OR with Y, exclusive OR with the C in. Okay, what does this tell us? It tells us that effectively I can use a full adder to perform an exclusive OR operation with 3 numbers. Okay, so right now what I'm going to do is I'm going to use this to solve our current question here. So what I can do is I can say that for each adder, for each full adder, I have 2 inputs here, X, Y. I have 3 inputs, X, Y, and C in. And now what I'm going to connect, for each of the inputs here, X and Y, I can connect maybe X2 and Y2. Okay, and the sum here is basically going to give me the operation of X2 exclusive OR with Y2. Now, before I proceed, we saw that it is actually an exclusive OR operation of 3 inputs, correct? So there is also a C in over here. Now, what value should the C in be tied to? Okay, so in order for us to understand this, let's look at the exclusive OR gate again. So if I look at exclusive OR gate, okay, now if I have an input X and I have another input here which is tied to 0, then the output here is going to be X exclusive OR 0. Okay, now let's analyze this a bit. If my X here is a 1, then 1 exclusive OR 0 is going to give me a 1. Correct? If my input here, okay, is going to be 0, 0 exclusive OR 0 is also going to give me a 0. So what do we see here? We see that if I exclusive OR with a 0, the original data is retained. Okay, if I exclusive OR with a 0, the original data is retained. So nothing changes by doing an exclusive OR with a 0. So that is why the third input here must be tied to a 0. Okay, so though I have an exclusive OR with 0, it does not affect this result in any way. Okay, so this is the result I'm interested in. The exclusive OR with 0 does not matter at all. Okay, so I just repeat this whole process 3 times for the 3 full adders. Okay, so again I have x, y, and c in here, and I have another x, y, and c in over here. Okay, so this is your x1 and y1, and this is your x0 and y0, and each of this is tied to a 0. Okay, and now I need to do a addition. Okay, so if you look back over here, what did we do in this stage over here is, after I do exclusive or bit by bit, I need to count the number of ones. Okay, so I need to add this bit with this bit with this bit to see what's the final answer. So what I'm going to do now is I'm now going to connect all of this to another full adder. Okay, so the full adder has x, y, and c in. Okay, so this one comes here, this one comes here. This is your x1 exclusive OR with y1, and this is your x0 exclusive OR with y0. Okay, and the output of this would be 2 bits, your sum and your carry. Okay, so we saw that the only possible answer that can accept is 1. Okay, so 1 in 2 bit is basically 0 1. Correct? 1 in 2 bit is 0 1. So carry must be 0 and sum must be 1. So effectively the only possible solution is this. Okay, this is your n. So as long as carry is 0 and s is 1, then this n will be a 1. Okay, carry 0 and s is 1, then n will be 1. Okay, so this is how we can go about solving our question 2. Okay, so in order to solve such questions, okay, first thing is we must understand what we are trying to do. Okay, so we must analyze the K-map and understand that the neighbors have only a single bit difference, and to get this difference I must do an exclusive OR. After I do an exclusive OR bit by bit, then I need to add up all the results, and the final answer of the addition can only be 1. Okay, because I can only accept a value of 1 to indicate that they are neighbors in a K-map. Okay, so I hope the solution to question 2 is clear with this explanation. Okay, now let's go on to question 3. Okay, in question 3, basically what we are trying to do is to detect if a given number is a biquinary code. Okay, so what is a biquinary code? Okay, from the numbers given, you can see that you have, okay, a 7-digit number. Okay, and this 7-digit number is represented with these letters here: P, Q, R, S, T, U, V. And if you look at it, the first 2 bits here, P and Q, will occupy the values either 0, 1 or 1, 0. And for the remaining 5 bits, R, S, T, U, V, what do you observe is that you must only have a single 1, okay, in this 5-bit value here. Okay, so within this RSTUV 5-bit value, only one of these bits should be a 1. The rest of it must be 0. Okay, if both of these conditions are satisfied, condition 1, okay, and condition 2, then we say that this is a valid biquinary code. Okay, so this tells us 2 things. Okay, in order for me to detect if a 7-bit value is a biquinary number, I need to first look at the upper 2 bits P and Q and detect if they are either 0, 1 or 1, 0. Okay, that is the first thing. And from RSTUV, I must see that it's only a single 1 in this 5-bit value. Now that we understand that we need to check for these 2 conditions, let's see how we can do each of them separately. For this first condition, 0, 1 or 1, 0, we know that this is actually equivalent to a exclusive OR operation. Okay, and for this RSTUV, basically what I need to do is to count the number of ones. Okay, count the number of ones, okay, inside this RSTUV bits, and the only possible answer is, okay, only acceptable answer equals to 1. Okay, because only a single bit must be 1, the rest must be 0. Okay, so these are two things I must do. For the first one, exclusive OR operation, we have already seen that a full adder actually does a exclusive OR operation of the three inputs. Okay, so we have X, Y, and C in. So what I can do is I can connect my P and Q, and the third C in I can put a 0. So the sum over here is nothing more than P exclusive OR with Q. Okay, as we have seen in the earlier question, an exclusive OR with 0 does not change anything. So the sum is actually an exclusive OR operation. So I want this to be a 1 to indicate that both the bits are either 0, 1 or 1, 0. Okay, so for the next set of the next condition, which is to basically count the number of ones, okay, we have also seen that I can do it by using full adders, okay, to count them as individual bits. Okay, so what I can do is I can have another two full adders here, full adder here, and another full adder here, and this I have X, Y, and C in, another X, Y, and C in, and what I'm going to do is the inputs to this are the 5 bits that I have. Okay, and the 5 bits that I have are RS, R, S, T, U, V, and this last one C in I can put as a 0. Okay, so basically what I have now is that this two full adders are going to add up the RSTUV as individual bits. Okay, and they're going to provide me with 2-bit answers. So for this, I'm going to have a sum and carry out, and for this second, I'm going to have another sum and carry out. So it's very similar to what we did in the earlier question. Okay, and now I need to sum up this and this together. Okay, so I'm now going to make use of the 2-bit adder. So the 2-bit adder that I have, okay, is going to take in two 2-bit numbers, x1, x0, and y1, y0. Okay, and I'm going to connect them this way. So the carry is always the upper bit and the sum is the lower bit. Okay, and of course in this case the carry in for the 2-bit, I'm just going to assign it to 0 because there's no carry in. And basically what does the 2-bit adder do? The 2-bit adder is going to add up the number of ones generated from RST and UV all added up together, and the answer of this is going to be a 3-bit number, which is basically your sum 1 sum 0 together with your carry out. Okay, and as we have seen earlier, the only acceptable answer is 1. Okay, so if I look at C out, S1 and S0, the only acceptable answer is 0, 0, and 1. Okay, 0, 0, and 1. So what I'm going to do is I'm going to put this into an AND gate here, where this C out must be a 0, this S1 must be a 0, and my S0 must be a 1. Okay, and the other condition is that this exclusive OR must also be set, correct? So this is also connected here as another input. Okay, so the output of this AND gate here will be indicating if it is a valid binary number. Okay, so if you look at this solution, basically it has two parts to it. Okay, so the first part over here is basically checking on this, whether there is a exclusive OR between P and Q. That means you're either 0, 1 or 1, 0. And this second part over here is basically doing this checking here to see if to count the number of ones that I have, and and the only acceptable answer is 1, 0, 0, 1. So if when I get 0, 0, 1 over here, what I will get is this will be equivalent to a 1, logic 1 here, logic 1 here, logic 1 here, and this also is a 1, so it's valid. Okay, so why I say logic 1 here is because if this is 0 and this is active low input, is equivalent to a valid 1 input here for the AND gate. Okay, so that is a valid, this will make the output of the AND gate 1. Okay, and this is how you solve the question 3. Okay, so now we have seen question 3. Let's go on to question 4. In question 4, basically what we have is a 0 enable 2 to 4 decoder. So let's draw the decoder first. Okay, so we have two inputs, S1, S0, and 0 enable. That means this is active low. And we also have negated outputs. So the outputs are 0, 1, 2, 3. So these are negated outputs. Okay. Now, what we are asked to do is to implement this Boolean function J, W, X, Y, Z as the max term of 2, 3, 6, 7. Okay, so what we can do is we can draw our K-map first, okay, to see what is the simplified expression that we get. Okay, so if I to draw the K-map, okay, so let's take some time to draw this out nicely. So we have WX, YZ. Okay, so 2, 3. Okay, so let me put the numbers first. 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0. Okay, so 2 is this. So the max term means these are the zeros. So 0, 2, 3, 6, and 7. Okay, so the rest of them are all ones. Okay, the rest are all ones. Now let's look back at this again. So we know that this is your K-map for your J. So if I group the ones, it is giving me a min-term expression for J directly. Correct? But if I group the zeros, then what I'm getting is a min-term expression for J bar. Correct? Okay, so this is something we saw in the last tutorial. So if I group the zeros together, okay, what I get is this is basically W bar and Y. And since I'm grouping the zeros, this is actually J bar. J bar equals to W bar Y. Okay, so if J bar equals W bar Y, we can rewrite it as J equals to W bar Y with a bar on top. Correct? Okay, now let's look back at our 2 to 4 decoder. Now, if I were to put W and Y over here, what do I get at the outputs? If you recall, a decoder's outputs are basically its min-term expressions. Correct? So this is actually 0, 0, 0, 1, 1, 0, 1, 1. So this is W bar, Y bar. Okay, this is your W bar Y. This is your W Y bar, and this is your W Y. Okay, so this is how it is rightfully written. But since these are active low outputs or negated outputs, that means I need to add a bar on top of each of it. Okay, and now what do you see? You see that this term here is the same as this. Okay, so this is actually your J. Okay, so all I need to do is connect W and Y to S1 and S0. Make sure the enable is tied to a 0 to enable the decoder, and my output is actually from line 1 over here, which is W bar Y with a bar on top. Okay, so it is a very easy and direct translation as long as you understand how the decoder works and how the K-map works in terms of the max term expression. Okay, so that is your question 4. Now let's go on to the next question. So in question 5, we are asked to uh, solve this expression, okay, where f is given as this, okay, as a min term expression, and we're supposed to implement it using the least number of 2 to 4 decoders, okay, with a single one enable and normal outputs, and at most 2 logic gates. Okay, how do we go about doing this? So the first step is, of course, we can draw our k-map. Okay, so let's draw our k-map to get a simplified expression for this. So f a b c d. Okay, so let's put in all the numbers first. Okay, 0 0 0 1 1 1 1 0 0 0 1 1 1 1 0. Okay, and basically you will see that is 1 1 1 0 1 0 1 1 1 0 1 1 1 1 1 0 here. Okay, now in terms of groupings, okay, as we have seen before, you can either consider grouping zeros or grouping ones. Okay, either way is fine. And in this case, since grouping the zeros, I only get 2 terms, I would look at the grouping zeros as a better option. Okay, so how would I go about it? So I have one group here and I have another group here. Okay, so this group here is basically my C bar D and your B, and this grouping here is your B bar C D bar. Okay, now once I know these two grouping, how do I proceed? So we know that, again, if I group the zeros in a k-map, it is actually the expression of f bar in terms of a min term expression. So I have B C bar D plus B bar C D bar. Okay, and now since I want the expression for f, what I can do is I can put a bar here and I can put a bar here. So effectively what happens is f is equals to B C bar D plus B bar C D bar, but with a bar on top. Okay, now how do I implement this? Using my decoders. Okay, so there are many different possible solutions. Okay, so I'm just going to show you one first that involves 2 decoders. So for the 2 decoder approach, what I'm going to do is I have S1, S0 here, and I have E. I have another S1, S0 here with the E. Okay, now what I'm going to do is I have my inputs here B, D, and C. Okay, and I'm going to connect the C to this enable. So if C is 1, this decoder is enabled. Okay, that means I am now referring to this combination here. So C is 1 means what I want is I want B and D both to be 0. Correct? So if I connect B and D here, when B and D are both 0, then the line 0 is activated. Correct? So that is the line that I want. Okay, so again, looking back at this, how I came to this is, in this case C is 1 and B must be 0 and D must be 0, which refers to this 0 1 0 over here. Correct? So in this situation, 0 0 means line 0 is activated and C is 1 means this decoder is enabled. Now for the other decoder, again, yeah, there is no fixed approach. You can look at it in your own way. So I can connect B to this enable. You can also have chosen D. It's also fine. Okay, but now I'm just saying that I'm using B to connect to the enable. So when B is a 1, okay, so when B is a 1, then this line is activated. So when B is a 1, I want C to be 0 and I want D to be 1. Okay, so again, it all depends on how you wire up the things. So I can connect the C to S1, okay, and I can connect the D to S0. Okay, so in this case, C must be 0. Okay, C must be 0, and D must be a 1. So in this case, the line 1 is the one that's activated. Okay, and what do I do after that? Either this combination or this combination must go through a NOR gate. Okay, so I draw a NOR gate over here. Okay, and that is your F. Okay, so this is only one possible solution. If you had wired up B, C, and D differently, then you may have a different sort of connection. But ultimately, what is important is you are fulfilling the combination that is already in your expression, which is B, C bar D, or B bar C D bar, and you pass through a NOR gate after that. So depending on how you wire up, you may have taken different outputs of your decoder. Okay, so this is one possible solution. Now let's look at another possible solution. So another possible solution is, again, let me write the expression first. So the expression is F is equals to B C bar D plus B bar C D bar, and I have a bar on top. Okay, so one thing you can note from observation is B and D is either both 0 0 or both 1 1. Okay, so that means either when B and D are both 1 or they are both 0, then I look at C or look at C bar. Correct? Now, how do I make use of that in my design? So we know that we can make use of a XNOR gate to detect if both bits are the same. XOR will detect if both bits are different. XNOR will detect that both bits are the same. So let me just show you through the truth table. So BD and output here. So 0 0 0 1 1 0 1 1. Okay. So for XNOR, this and this will be a 1, this will be a 0. Okay, so what I can do is the similar approach. Okay, but now I look at the decoder and the enable S1 and S0, and what I can do is I can connect D over here and pass D to a XNOR gate, and this is your B. Okay, so basically what will happen, only when they are both 0 0 or 1 1, it will get activated. Okay, so it's either both of them are zeros or both of them are ones. Okay, and the other input over here, I can tie it to C. Okay, so now let's look at the possible combination. So either D is when B is 0, okay, D is also 0, and that means C must be a 1, correct? When B and D are both 0, C must be a 1. Okay, so in that situation, 1 0 is line 2. Okay, so this is the case where it is B bar, C, and D bar. Okay, C is a 1, D is a 0, and B is also 0. The other situation is when both of them are 1s. So when both of them are 1s, B and D are 1, C must be a 0. So in that case, when it's a 1 and 1 and it's a 1, C must be a 0. Okay, so 0 1 means the line is line 1. Okay, and that is the combination of B, C bar, D. Okay, and then again I pass through a NOR gate, and that is my output here. So again, there are many other possible solutions depending on how you have chosen to design and how you design the system, as well as how you've decided to connect or which bits you have used to connect to the inputs of the decoders or the gates. Okay, so your design may be slightly different, but the idea is the same. Okay, so once you get the expression for f, you try to implement it using the hardware that is given, which is your decoder as well as the least at most two logic gates. Right, so in this situation we have one decoder and two logic gates. Okay, so I hope that with this tutorial you have a understanding now of how I can use adders to count ones. Okay, how I can use adders to do XOR operations, and how I can from a K-map do a simplification and then use decoders and logic gates, to sort of simplify and get the final answer that I want. Okay, so thank you, and I will meet you again in the next video. Thank you.